Let's get started on chapter 7.5, which is about work and energy and force and power. So you might ask, why should we work on this chapter? Well, it's again another chance to break a big problem into small little problems and then add them all up, probably using an integral. It's also a prelude to something in Calc 3 called line integrals and path integrals. And also it's a good chance to work on our scientific literacy about important things about electric power and stuff in our society. So we're going to start with a quick overview of some physics. So force is measured in pounds or newtons. Pounds in the US system. We're going to focus on newtons in metric system. So 1 newton is defined as 1 kilogram per kilogram times meter per second squared. And we'll look at that in more detail later. Big question, is 1 newton a lot of force? Well, on Earth, if you just think of 1 kilogram, that the amount of force that needs to keep it from falling, for example, is 1 kilogram times how much gravity accelerates things. So that would be 9.8 newtons for 1 kilogram, which is about 10 newtons. So you could say that 1 newton is about 1/10 of a kilogram's worth of weight, which is about 100 grams here on Earth. I'm not sure where you're watching this from. So what weighs about 100 grams? It turns out a small apple, I weighed this one, it's just over 100 grams. So it takes 1 newton of force to keep this from falling toward the Earth. So a newton is not very much force. Let's talk about how much work it takes to move things around, or how much energy we expend in doing it. There's a physics definition that the work it takes to move something is the force applied to it times the distance that you're moving that thing. Not the time spent moving it, but the distance. And I'll let your physics professor explain more about that. Let's take a quick example. Let's say you have a really heavy piece of furniture and you're moving it up a staircase. Most staircases are somewhat more than 2 meters, but let's say it's just like a basement staircase or something, and it's on Earth. How much work is done just using this formula? So we'd say the force applied is what, 100? So times the distance moved. Is the force applied 100 kilograms? No, kilograms is a mass. To convert to force, we have to say how hard is the Earth pulling on things, 9.8 meters per second squared per kilogram, roughly. So the force applied would be 100 kilograms times 9.8 meters per second squared. And then the distance moved, we just said 2 meters. So that would be, let's treat this as 10, 9.8 is 10 mentally. So it'd be 10 times 100 is 1,000 times 2. So that'd be roughly 2,000 newtons. Kilogram meter squared is newton times meters. So that's the amount of work done to move a fairly heavy piece of furniture up 2 meters. We should talk briefly about robot arms versus human arms, or animal arms in general. This formula means, and we'll interpret this later, this formula means that if you're applying a force but not moving any distance, so if I'm just holding this apple but not moving it up or down or left or right, if I'm just holding it here, I'm applying a force to it, but the distance that it's moving is 0, so I'm not doing any work, and in theory not expending any energy. But do you think I could hold this here for 24 hours straight? Do you think my arm would get pretty tired? Yeah, probably, right? Especially if it was heavier. That's because the way that animal arms work is they have to expend energy continuously just to keep the same length on the muscles. Sorry to veer into biology here. But if you think of arms as robot arms, once they move to a certain position, they can turn their motors off, and it's just held in place by like the friction of the gears and anti-backlash things. So when we think about applying energy or work to move something around, it's actually kind of better to think about it in terms of robot arms, where you're putting some energy into the system, some electricity to move the motor, and then once you're done moving, you stop putting in any electricity and the thing just doesn't move. So in a lot of these problems, it's better to think about stuff in terms of robot arms. For example, if I'm not applying any force here and I move it over this way, I'm applying very little force to move it sideways, right? So that's saying the work done is basically 0 there. If I moved it back and forth a lot, I'd be expending almost just a little bit above zero repeatedly, and eventually I'd get tired. But people say, so you mean in moving something like a big heavy piece of furniture horizontally, I'm not really expending any energy? And if you move a 100 kilogram piece of furniture horizontally a ways, you're expending energy. That's because you're using human arms, hopefully. But if you had a robot just move it horizontally, it wouldn't need any energy to keep it where it is vertically. All right, so let's talk about whether this 2000 Newton meters, that would be the units here, right? Newtons times meters. Is that a lot? Well, there's an energy unit called a joule, which is 1 Newton meter. So this would be 2000 joules. So we can say that number right there is 2000 joules. An obvious question would be, is 1 joule a lot? Well, what can we think of that gives an energy of 1 Newton meter? That would be taking something that weighs a Newton and moving it vertically 1 meter. Does that take a lot of energy? Not really. Another way to think of it is, if I want to apply that much energy to something, I could drop this 1 Newton item onto my foot, for example, from a height of 1 meter. Would that hurt a lot? A little bit, but not a lot. So we could say it's like moving a small apple up 1 meter. Or letting a small apple fall on your foot from a height of 1 meter. Is 2000 joules a lot? What do you think? Well, by analogy, it's like moving a 100 kilogram piece of furniture up 2 meters. That takes a fair bit of energy. Or like letting a 100 kilogram thing fall on your foot from a height of 1 meter, which would probably not be a good idea, right? From a height of 2 meters, sorry. Now, if you want to get really detailed there, you'd have to talk about, well, is it made of something hard that transfers a lot of energy to your foot, or is it made of something soft that deforms and absorbs the energy itself when it hits your foot? So we're not going to get into that. But 1 joule doesn't seem like a lot of energy. 2000 joules would be a fair bit of energy. And then later we're going to be talking about megawatts and all kinds of fun stuff. In fact, let's go do that right now.